Hello everyone. It's been a while, but I'm finally back recording a video and finally just learning things again. So, a lot of my previous videos were doing some more like learning how transformer work. I don't know, I did like deep dives in C++. But it's time now to get back or get back to robotics and specifically robot learning. So what I wanted to do today is go deep into this Pi0 paper. Now this paper came out quite a few months ago. Actually, yeah, last year. So it's been almost a year, and it, it's there's not too much math, but I wanted to get into the math and first just like draw out the architecture, and then what I really wanted to do is dive into this flow matching loss and really understand how flow matching works. So there are these two papers. This is the original flow matching paper. I want to go deep into the math and actually really fundamentally understand it. I spent some time yesterday already like trying to understand parts of this, but there's still some like some minor details that I don't understand. So I'm going to be rereading this paper, and you guys can tag along and see how I study this. Okay, and I have a new setup today, so it will look like this. And if I open it, I have this. So usually I have my Obsidian set up like this, and I take the notes in Obsidian. But I also like think for specifically for like these equations, it's quite a bit faster to just like write it all up, right? Okay, so at a high level, what is Pi0? Pi0 is this like vision language action model, and it has if we like look at this high level diagram, right? This sort of talks about how this model was trained on cross embodiment robot data set. What that just means is that it's been trained on different robots, and so you have here. This is a UR5. These are UR5s, and then there's some Aloha robots, and then they trained on all these different tasks, right? And so you'll see here what's interesting is I believe some of them are a single arm and some of them are bimanual. And then what they'll do is they'll take a pre-trained VLM and they'll just slap on an action expert, right? And really that's all Pi0 really is. And then the interesting part, I guess, is how this action expert is implemented, right? And they use flow matching to do this. And then they do post-training. So once you have all this, you take a VLM, you have an action expert, you pre-train it with all this large-scale data set using OpenX embodiment data set. This is a huge data set that Google released. OpenX embodiment. Yeah, it was by DeepMind. DeepMind released this. And so they take that, and I assume this internet scale pre-training, it refers to how the VLM is trained. They take the OpenX data set and they pre-train it. And then to make it work well on a specific robot, they will do post-training. So what that means is just that you will feed it robot-specific data. So let's say you have this robot that you wanted to do like t-shirt folding in this case, I guess, or folding pants. You'll collect some data on this robot station and fine-tune your model. And then I guess what they claim is that it can zero shot in distribution tasks. And so what that means is, I guess if you have the same task in a new setup, you can zero shot it. Specialized post-training to difficult tasks. Or efficient post-training. Okay, I guess these are just like I don't know what this means. Specialized post-training to difficult tasks. I mean, yeah, all these are just post-training. You need to post-train it. Is essentially what this says. Okay, so let's look at the architecture. So what they use for the VLM is Polygemma. And so, yeah, there's Suglip and Gemma. All right, so Polygemma. And so Polygemma is a model used by, I believe, released by Google as well. And the architecture of Polygemma oops. Oh, I'm also in the wrong screen. Okay, I need to, yeah, we're in this screen right now. I'm not writing any equations so far, just giving you a high level overview of how this looks. How polynomial looks, I am not particularly familiar, but it is the VLM, right? And what they'll do is they'll add tokens, extra token. So they'll describe it here is robots. That's a token. Essentially, there's a set of tokens. I believe they mention it here. So the Pi0 consists of a VLM, right? Though it consists of an image encoder with the same embedding space as language tokens, and then you further augment this backbone with robotic-specific inputs and outputs, right? And so proprioceptive state and robot action. So proprioceptive state is just like this current state of the robot. So these are like the joint measurements. And then I guess outputs will be the actions. And then conditional flow matching is what we are interested in looking at, right? So this is the loss. How do you train your model? And by the way, like all of this is imitation learning, right? So what we're doing is we have these demonstrations of how things are done, and our model is going to predict how these our model is going to learn to basically imitate whatever this expert demonstration is. And back to the tokens, right? So they're gonna, what they'll do is just like, and this is I think pretty common, is you have VLM and you introduce these special tokens and you train these special tokens, use these special tokens for different things. So in this case, sorry, I'm scrolling like all over the place. We augment this backbone with robotic specific inputs and outputs, namely proprioceptive state and robot actions. And then they use full matching, and then you're using a separate set of weights for the robot specific tokens led to an improvement in performance. Okay. All right, and then this is the formalization, which we're gonna get into in a second. And this talks about data collection. I think the data collection, I mean, it's interesting, but from our perspective, like we want to focus today on the modeling side. And these are some more experiments. So it's not a very technical paper. Like I guess like the only equations that we're really interested in is here. And I believe actually they have released an open source version. So we can potentially look at this, although it is written in JAX, I believe. And I don't really know JAX. Oh, they have a Libero. Okay, I'm working on Libero, so good to know. Set the init state. Okay. Yeah. Let's go back here. And yeah, there's a vision transformer here. So this is just encoding the image into some token space. And then the text is also just tokenized, right? And so these are, if you forgot, how does the process of tokenization work? I mean, tokenization is just this process of mapping, I guess like breaking this text into sub-chunks, right? So like fold might be, the one token would be FOL, and that might maps to some index in your embedding table, right? And each of the tokens, indices will map to specific embedding, right? And the embedding is actually what is used to do your, that's actually like a vector that's used for training, right? So the tokens are just like indices, but tokenization is this process of like converting your tokens into some embedding. That's not fully correct. Tokenization is the process of, I guess, like breaking it down into tokens, and once you have your tokens, then you can use it as an index into your embedding table. Okay, that makes more sense. Okay, so let's just quickly redraw. I think the main thing that's confusing for me, or was confusing. Okay, so let's just draw this, right? So what we have is we have a bunch of, and I'll draw this like in a different way. I'll draw this like top down. And now let's switch to our iPad, right? So if we can just like briefly describe the Pi0 architecture, right? So what they do is you take a bunch of images, and here you see 3 images because these are 3 different like camera angles, right? And notice here that they're only taking an image at the current time step, right? So like what people could also do is like, instead of taking a single image, take a history of images, right? And I guess like why didn't they do this? One is like a lot more overhead. I mean, and people have done this, but in this paper specifically, they don't do it, right? So if you know, each of these images like are actually quite big, right? So I think did they talk about like what dimension? Image resolution. Yeah, is there a paper here? Source Open Pi models. Their tokenizer is here. Pi0. Their vision transformer is here. Is there a config file they have? You can probably see in the config file. Model. Okay, so yeah, the image resolution as input that they use is 224 by 224. So each of these images are 224 by 224. All right, and what you'll do, and these are pixels, right? I buy like 3 because they're RGB, right? And so I guess like this is the dimension, right? 224, 224, 3, 224, 224. 224, 224, 3, right? And so these are your images, right? And then you have your text prompt. So for example, in their example, they have fold t-shirt, right? T-shirt. They all have your proprio state. So these could be like joint. These are like the joint angles. So if it's a 7th off or 6th off, yeah, it's probably a 6th off. So it's like 6 joint angles, right? So I don't know, like 20 or I don't know, some like arbitrary number, 0 0.3, 0 0.71, 0 0.8. All right, and then is there one more? No. So these are actually your only 3 inputs, right, into your model. And then you have a VLM, right? So your VLM, right, what does it take? All right, so we have essentially this huge right, so how do we represent this? So like your VLM is like expects, I don't know, like a list of tokens, right? And then each token gets mapped to an embedding vector, right? So the tokenizer, this is like we know how a LLM works, right? So we understand that it's translating this, tokenizing it. This tokenization happens like let me use a different color, like maybe full, and then T, sure. Okay, maybe it goes like this, and then this maps to like some embedding vector. I think I'm referring to my mental model of how a transformer works. So in this drawing, right, we have some text, and we map it to some index, and then this gets mapped into, you look at your embedding matrix, and then this is your input embedding, right? And so these are essentially like these, how do I like cursor? Do I have a pointer here? Oh. I don't have a pointer. Oh, like this. Okay, yeah. It's these. Each of these are like one of these input embeddings, right? And so these are what actually get fed into the model. And like there's a positional encoding, but like that doesn't really like that's fixed. That's a fixed matrix, right? So these, let's say like these go here, or I guess like your images, right? So like they need to map to some embedding matrix. Wait, before we do that, like let's say these will go into here, right? And then the proprio state, like your VLM, so maybe like let's first spend some time trying to understand how this VLM is like, like how does it accept these tokens, which I'm not super familiar with. Right, so they use a sentence piece, I guess. It seems like what they use, sentence piece, because this is like Pi0. Right, so this is a sentence piece. Oh, and I realize you guys don't see this super well. It seems like they use sentence piece. Let me move this like here. Okay, they use sentence piece, and then for the it's some linear projection, contrastive vision encoder. Yeah, but I guess like what happens is some of these tokens, so some of these, right, will be reserved for text, right? So let's say this chunk of tokens will be reserved for text, and this chunk will be reserved for images, right? And so, right, your image is of shape 224 by 224 by 3, which is quite big, right? And so, I don't know what each of these the embedding dimension. Yeah, so they project it. So the vocabulary of Gemma is 2 billion, right? There's 2 billion tokens. And more complicated alternatives, because they just do a linear projection. And hence decide to use. So tokens is image tokens, then, and there's a separator, prefix token, suffix EOS, okay. Yeah. Which is straightforward, making the image tokens. Yeah, so there's a BOS token here to mark the separation between images and text. Yeah, so it's probably, I think it's a Gemma. So Gemma has like 2 billion vocabulary. The vocab size is 256,000. So why is this saying Gemma 2B's vocab? Oh, it doesn't have 2 billion. Okay. Yeah, I was being delusional. It has a vocab size of that. Okay. Maybe I should make a note right now. Gemma. Yeah, and I'm making a note right now. Use piece as the tokenizer. Then these are our parameters. And Gemma is an LM. Okay. And so it has a vocabulary of 256,128. And so I guess like you have this, each of these images goes through some sort of like, it can be MLP, it can be you just call this an encoder, right? And so this just like takes the image as an input and learns to map it to these like, to the same space, that the text, right? How do you describe that? It projects it into the same dimension as the vocabulary, it projects the images into the same dimension as how the vocabulary in Pi0, the images get projected in the same dimension as text. Like, how do I explain this? In the same embedding dimension. Yeah, it's called the embedding dimension, right? So this is like the embedding dimension, and then this is, I guess, like times the number of embeddings that you can take, right? So how do I describe this in my transformer annotations? This is I guess your sequence length, right? Yeah, times your sequence length. So it's projected in the same dimension as the embedding dimension, but does it occupy multiple like embeddings, or is it a single embedding? So does the LLM take in multiple embeddings? Yeah, I guess. Oh, it is like over the patch, right? Right, because it doesn't make sense that each image only takes up like one embedding, a token. Does an LLM take in a sequence of tokens or a sequence of embeddings? Like it's a sequence of tokens that can map to a sequence of embeddings, right? Yeah. And there's an embedding matrix. For the images to get mapped to token indices, then yeah, it doesn't make sense for them to map to token indices. Like it's like, imagine mapping it to like the words BOS, like that doesn't, or like the character, so like DSH or something, like some random characters, right? Like rather you just want you make this a linear projection, project it into the same dimension, and then use however many patches you need. And yeah, this contrastive vision encoder is, I don't understand this. What is this contrastive? Oh yeah, so siglib is trained separately, I think, right? So it's just, they take siglib. So they essentially, so in Pali, they take a pre-trained siglib, which is trained to based on a contrast, and then this siglib maps to some space, and then a linear projection is done to get to the right embedding dimension as what the text tokens get mapped into. Is that correct? Wow, okay. I mean, oh wait, I don't believe it fully. To freeze or not to freeze. Yeah, so I guess it is frozen. That means that the weights are not updated for the image encoder, and the image encoder is siglib. And how siglib is implemented, I have no idea. But you can imagine it's some big transformer, right? Like, I guess we can quickly look at how siglib is implemented. Is implemented with a vision transformer. And so with the vision transformer, I guess like we need to understand how a vision transformer works. Yeah, essentially these are vision transformers, right? And they get projected into some, is that right? Yeah. In the case of text, you don't have the concept of a transformer. You just literally take your token or take your text. You have a tokenizer, right? That's been trained, and we understand how a tokenizer works. If you don't, look it up. It's pretty simple. Like, or you can look at my notes on tokenizer. Right, and then yeah, and usually learn is not, you look at byte pair encoding essentially. This is essentially what it's being done, and yeah, so you just look up this embedding. You have your tokenizer, you map it to some indices, and then you have an embedding matrix that you use, right? And this is gonna be like, each of them is a token, and then there's some embedding, right? So that's for your text. You don't need some transformer. But for the images, you have these, you take these patches of the image, and you need to learn to project it into some dimension, right? And so your vision transformer's input will be, maybe it's worthwhile to spend some time on this. It's something like this. So you take your image, it will be, you split it up into these small patches, right? So you have an image. I'm just gonna draw this, but erase this. You have an image, and let's take another out. You have an image, you're gonna chop it up into these patches, and how big these patches are will be, you'll determine this. This is like a configuration that you can decide. And so for each of these patches, now you have these smaller patches, right? And so what do? They do some linear projection. Okay. What does that mean, linear projection? I guess like you just reduce the dimension of your images. Siglet does it. Yeah, so each of these image patches is going to be flattened, right? So if you flatten it out and then you multiply, you go through some encoder, or this is just a linear projection, and it'll be like end up with like, it'll be a smaller number. And then you need to, now you sort of like lost information about how each of these patches relate to each other, right? But you'll have this later on with like your attention mechanism, right? But you still want some sort of like positional encoding, right? And so you're gonna have this plus some positional encoding, like that's your sinusoidal encoding. Okay. And then you feed it to your transformer. And so there's no concept of, I guess like you can think of each of these as like, there's no like concept of like an embedding matrix necessarily, right? You just like multiply it by some encoder, right? And the encoder generally just reduces the dimension of your input, right? Yeah, that's right. And then what it outputs, right? So you go through this, and then you're gonna have a transformer, right? And then what you're gonna output is some like latent representation of what these images represent, right? How big feature embedding? And I guess the dimension of that, it's like, doesn't really matter. Like in the context of like LLMs, like the output is just like, the output is the next token prediction, right? And then so you have like your loss is the cross entropy loss, I believe, right? So 16 for 16 by 16 patch. So it's 16 times 16 is 256. Isn't that like pretty big? Isn't 76 more than just the pixel? Yeah, why would you want it to be bigger? Yeah, okay, I guess multiply by 3 is 768 is essentially RGB. You just flatten it. Do you even need this linear projection? Why is the linear projection layer needed? Just pass the raw image. Right? Like, yeah, the raw pixels are not expressive enough. It acts like a shallow CNN, I guess. Okay. But it's linear. It's linear. What can it possibly do? It's like, is it like a convolution? I guess it's just to help the model, right? So things like edges and separate color channels more meaningfully, but like make it easier for the model to learn, I guess, right? Like it's not particularly necessary. Enables. I guess like within the patch. Positional embedding, not positional encoder. I guess like patch wise. Positional encoding help the model understand the relative ordering of the patches. However, within a patch, how is the spatial relationship learned? Yeah, okay. With large datasets, pure bits perform well. We don't need convolution if we scale up data and compute. Convolutions are much better at extracting. They're more sample efficient, I guess, but they cannot learn deeper representations. Okay, wait, we're going down a different rabbit hole right now. But I guess we understand, like, we have these images, there's these patches, and you have each of these patches of images get flattened. Okay, maybe query. Create a new drawing and embed. Okay, so we have an image. Vision transformer takes an image. Then you have these converted into these patches. And then with each of these patches, you're going to with each of these patches, they're going to go through I guess like I should just like duplicate this. And I want this to be an arrow, but it's too big. No. Can I make this smaller? Or maybe I make this thicker. Okay, maybe this is like more intuitive. Flatten. So let's say, yeah, the original image is like 256 by 256. No, by 3. No, that's okay. Let's say it's 64 by 64 by 3. Cut it into 4 patches. Each of them is 16 by 16 by 3. And so you end up with like 768 by 1. Yeah. And then what you're gonna do is have this go through a linear projection. Into, this is like, what do I call it? LD transformer. Sure. Okay, channel length. Yo, I don't know why I call it C. I feel like D is better. Oh, because here, huh, because yeah, you do multi-head attention. So here it's sequence length by channel size. And then you're going to split this into multiple heads. No, LD. Yeah, I started using LD. Okay. Alright guys, give me a second. I need to replace everything by D. Okay, and multi-head attention. Okay, so yeah, we have, let's go back here, and then I guess this is like D by 1. I guess it's 1 by 768. I'm kind of stupid, huh? I guess you could just do like this. And that's pretty much it, right? So you have your linear projection, some positional encoding, and then that's your transformer. Okay, cool. You have your linear projection, and then, yeah, position encoding, and then, okay, and then it goes through a transformer, and then whatever the output is whatever the output is, right? Oh, and then they do multi-class classification. Okay, that's funny. All right, so we understand all of that. The images, simply, you take the patches, you linearize them, there's some positional encoding, and then it gets projected into some output. Oh my god, wait, I was sharing the wrong screen this whole time. Oh my god, I'm sorry guys. Oh no, I was fine actually. I was just like, probably I should have done this screen. Okay, I apologize, guys. Okay. Oh, anyways. So we're back to the Pi0 architecture. All right, so this pre-trained BLM, if we go back to my drawing, it kind of looks like this. We have, oh, this is getting messy, right? But you have your images, your text prompt, and your proprio state. And each of these, I guess like I can use a better color to separate them. Right? Each of these, so image and text, this is just Pi0. But now we add in this proprio state. And these probably, I assume, are gonna be mapped linearly or some way. Yeah. Okay, this is what I wanted to describe. Pi0 or Pi. Our encoded proprioceptive state. So they're encoded and then they're going to be projected into the same embedding space as the language tokens. Is that it's siglip, and is there, did I just write down somewhere? It gets images get mapped into the same embedding space as the text. Also see Pi0 how I explain this. Okay. And then wait, where's my water? Move this. Make this even smaller. Yeah, make this like really, really small. Okay, so we were saying the images. Your Pi0. Okay, erase this, erase all of this. And so Pi0 is trained by like this. You have the images, goes through siglip, and then gets mapped into the same space as the text tokens. Now, specifically how it works is like you have these image patches. I guess like you need to look at siglip. I guess I got a mental model of like how a vision transformer is. And then the loss, and then use a contrastive loss. Yeah, it's using contrastive loss, so I guess like guess that, like, it does that, I guess. Siglib just does that, but the loss is used to maximize, like, it's using contrastive loss. And what is contrastive loss? Is essentially loss to minimize, oh, what is contrastive loss? Oh my god, guys, I don't know what contrastive, oh my god. Oh my god. I need to go to bed now, huh? Sorry, guys. Oh, I'm supposed to be sleeping at 10. Okay, we're gonna go for 30 more minutes. My screen time went out a bit. Okay, I should be good now. Okay. Alright, I'm back. Whoops. So we were supposed to go to normalizing flows, but essentially this is just a vision transformer, and then there's some linear projection to make it work between Gemma's or like Siglib's transformer, like embedding. Like, I guess there's a mismatch between the like what the numbers mean in the embedding that was trained in Siglib versus what the token embedding dimension, like the token embeddings mean, right? So they exist in them a different space. It's like saying like 5 might mean a different, like the vector 100 might mean completely different things on two models that have been trained in a different way. And so for them to map to each other, you need this like linear projection to happen, I suppose. And then once you do that, then the images will be projected in the same space as what the text, the same embedding space as what the tokens were trained to be on. Okay, so given that, we can now look at our flow matching loss, right? So plus the interesting part is this action expert, which I've like not even gone into. Right? And this is actually the interesting part, right? So this proprio state is just like you essentially extend polygemma, increase, I guess, its sequence length, or I guess like you clip off the text prompt and then just have this proprio state get encoded similarly to how images are, but this is probably a lot more lightweight encoder, and this is probably just an MLP, and it gets mapped into some embedding dimension, right? So it doesn't go to the tokenizer. Sorry, this is like kind of hard to. This is an MLP, and it gets like mapped into the same embedding space as the text tokens, right? Now, the question is still like, how many, when the images are, is each patch in the image the same as the token? Yes, so each patch. All right, so the smaller your patches, like the more tokens you're gonna eat up. Each patch. Okay. Each patch is like a token. This is particularly important when you are looking. longer the required. Okay, so yeah, this could be done better. Okay, the flow matching loss. Let's talk about that because that's what I've been trying to get to. But before we even get that, one thing to note with what Pi0 does is that instead of predicting one action, what they do is something called action chunking, which is just a really fancy term for saying you're predicting a sequence of actions as opposed to one action, right? So you're predicting a chunk of actions. So let's look over here for the notation. I'm going to write down all of this notation. So we have AT is equal to AT plus 1, dot, 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 AT plus H, right? So when we have this AT, remember this is just at time step T, we're going to be predicting a chunk of actions. That's the first notation we need to look at. And then so the input of the model is OT, right? The observation at time step T is going to be equal to the first image at time step T all the way up to the nth image at time step T. And then we're going to take our text prompt at time step T and our previous state at time step T, right? This is our input. And now we're going to be looking at, we feed this to the model, right? And then in which direction do we want our weights to be updated in? Well, our weights should be updated in a way that minimizes this loss, which is the conditional flow matching loss. And the conditional flow matching loss is going to be defined by this. And then I'm going to zoom out, make this slightly bigger. Actually, it's going to be defined by this. And yeah, it's going to be hard to see, so I'm just going to write this down. Right? So the loss, right, our goal is to minimize this loss. So it's going to be E of P of AT given OT, Q of AT tau given AT. And so this subscript was like also confusing for me, but the main thing that we're looking at is just really these two numbers. V, the vector field, and U of AT given AT. And so for this, we're going to need some background on like how diffusion works, but it's actually quite straightforward. Like I kind of got it, and I'm going to explain it to you guys in a second, right? So V sub data of AT tau given OT minus U of AT tau given AT, right? And then we're taking this squared. So really what's happening is this is going to be what our model predicts, and this is going to be the ground truth. Model prediction, ground truth, right? And so the way we define the ground truth, I'll say it here, U of AT tau given AT is equal to epsilon minus AT. Okay, so first let's get some background on like how diffusion works, right? So in diffusion, what's going to happen is we're going to sample from a Gaussian distribution, right? So it's we're going to sample some noise, right? And then we have some ground truth. So let's say our ground truth is like this perfect circle, right? So we need to train our model, right, to figure out how do we start from noise and get to some desired behavior, right? So we can call this noise epsilon, right? And in our case, the desired behavior is AT, right? This ground truth action. We need to somehow like start from like just pure noise and then get our model to learn what AT is. And so how do we go from epsilon to AT? Well, it is simply the difference between AT and epsilon, right? That's our ground truth. Like this arrow is what we want our model to learn, right? So how do we go from epsilon to AT? Well, it's just plus AT minus epsilon, right? So this vector is going to be equal, this vector is just AT minus epsilon. Is that right? Yes. And so in this case it's actually epsilon minus AT. Okay. okay, yeah. So that is the direction we need to go in. So why is u of at tau given at epsilon minus at? Well, I think this direction is going to be epsilon minus at. And so I guess like, so what are we learning? We're learning shouldn't our model be learning this direction? In which case it's actually at minus epsilon. So why is u of at, like why are we learning this? Like, okay, now I'm actually confused. Yeah, this is simply what the model outputs. The model outputs a velocity, because you can imagine at inference time, right? We only have access to the noise, and we need to predict at, right? And so we want our model to predict this velocity field. So I guess like, yeah, I guess that this is the noising. Isn't the denoising vector field actually at minus epsilon? And then, okay, before we go into that more, what's going to happen is at inference time, right? So once we know this vector field, right? So this is what v sub theta of at tau given our observation, what is at, what is the action that we should expect to see, right? And we could just this will be equal to epsilon plus epsilon at tau given ot, right? So this is just like one step. But you want to 10-step this, right? Which is like usually what you see in diffusion. So let's see my diffusion notes. Yeah, I guess like this image. All right. If we take 10 steps, yeah, I guess like this, right? Diffusion. Oh, that's wrong image. Right, like we want to essentially teach our model to go from more noise to less noise, right? And the loss, like, I'm confused. Okay. So noise. Yeah. Are you sure? Let's ask O3. Like maybe it's a bit more nuanced than this, right? And so how is flow matching different from diffusion? And what is conditional? Yeah, and then CNF. Continuous normalizing. Frick. Oh. Yeah. Okay, so they probably made a mistake. Okay. That seems like a very basic mistake. And in normalizing flow, what we learn is like an inverse mapping, right? So yeah, this is like exactly what we saw, right? This is essentially the flow matching loss, which is this. With like slightly, instead of u of t or u of x, it's u of at given at. Okay. Marginal probability, guys. What's marginal probability? Hmm. Okay, we'll continue this in a subsequent video.